Imagine you wake up in the 1990s, open a magazine, and see a mouse with what looks like a human ear growing out of its back. Naturally, your first thought is, humanity has lost the plot. Your second thought is, who gave Dr. Frankenstein a research grant? But here's the twist. That famous ear on a mouse was not genetic engineering. No one spliced ear genes into a rodent and created a tiny mammalian body horror side quest. What scientists actually did was far more precise and, in some ways, far more revolutionary. They used tissue engineering, combining living cartilage cells with a biodegradable scaffold shaped like an ear. And that single image, part science, part misunderstanding, part nightmare fuel, became one of the most iconic symbols of modern regenerative medicine. Tonight, we go down the rabbit hole, not the horror movie rabbit hole, the biomaterials rabbit hole. And by the end, you'll understand not just what happened on that mouse's back, but why this strange, unsettling experiment helped change the future of medicine. Act 1. The photograph that broke people's brains. There are scientific images, and then there are myth-making images. The double helix, Earthrise from the moon, the first X-ray of a hand. And then, somewhere in that hall of fame of human astonishment, sits the Vacanti mouse, a lab mouse carrying what looked like a human ear on its back. The picture spread because it was irresistible. It was disturbing. It was symbolic. It looked like proof that science had crossed some invisible line and kept walking. People saw the image and assumed the wildest things. They grew a human ear out of a mouse. They genetically modified the mouse. This is what happens when scientists stop fearing God and start buying polymer meshes. But the truth was less monstrous and more elegant. The ear wasn't a functioning human ear with hearing. It was an ear-shaped cartilage construct. In the landmark 1997 work, researchers described seeding chondrocytes, cartilage-producing cells, onto a synthetic biodegradable polymer shaped like a child's auricle, then implanting that construct to grow tissue in that shape, which means the mouse was not transformed into an ear factory by genetic manipulation. It was being used as a living incubator, which is still a sentence that sounds insane, but scientifically, very different. Act 2. What tissue engineering actually is. To understand why this mattered, you need to understand a brutal truth about the human body. Your body is miraculous. It is also wildly inconsistent at repairs. Skin? Pretty decent. Liver? A show-off. Bone? Respectable. Cartilage? Lazy. Whole organs? Absolutely not. And this is where tissue engineering enters like an overqualified architect. The basic idea is simple in concept and maddening in execution. You combine cells, scaffolds, and often biologically active signals to encourage the body to form new tissue. Think of it like building a house. Cells are the workers. Growth signals are the instructions. The scaffold is the frame. Without a scaffold, cells are like a construction crew dropped into an empty field with no blueprint, no beams, and one guy yelling, "Build me an ear." A scaffold gives them shape, support, a 3D environment, and, if designed well, a structure that gradually degrades as real tissue forms in its place. That's the genius. The scaffold is not the final tissue, it's the temporary choreography. It tells biology where to dance. Act 3. The ear was really a biological construction project. Now, let's zoom in. In the 1997 study, the researchers used a synthetic biodegradable polymer framework fashioned in the shape of a human ear, specifically modeled after a 3-year-old child's auricle. Then they seeded that framework with chondrocytes, the cartilage-producing cells. The mouse did not magically sprout an ear because someone inserted a make ear gene. Instead, scientists made the shape. They added the cells. The mouse's body provided a living environment, warmth, nutrients, blood supply around the implant, and time.
and the cells generated cartilage in the predefined form. So the real star of the show was not the mouse, it was the scaffold. The scaffold was the quiet mastermind, the stage manager behind the biological theater production. The mouse got all the publicity, but the polymer was doing the geometric heavy lifting. This is one of those moments in science where the public saw a miracle, but the actual breakthrough was engineering discipline. Not, can we create life? More, can we persuade cells to behave if we give them the right architecture? That is both less cinematic and more useful. Act 4. Why the world misunderstood it. Why did people leap to genetic engineering? Because humans are pattern-matching creatures with a dramatic streak. You show us a mouse with an ear-shaped object on its back, and our brains do not calmly say, "Ah yes, a biodegradable polymer seeded with chondrocytes." No, our brains say the apocalypse has a lab coat. But the confusion also reveals something deeper. People often collapse all advanced biology into one giant mental box labeled scientists doing weird things to organisms. Inside that box, cloning, tissue engineering, stem cells, gene editing, organoids, and glowing fish are all thrown together like a scientific junk drawer. But these are distinct fields. Genetic engineering changes the organism's genetic code. Tissue engineering focuses on building or regenerating tissue, using cells, materials, and structure. That distinction matters because it changes the ethical question. This wasn't about rewriting the mouse's DNA to manufacture novel anatomy. It was about learning whether living tissue could be shaped outside traditional developmental processes. That is a very different frontier. Still unsettling, but different. Act 5. The real dream behind the weirdness. The point was never to create a fashionable rodent. No researcher woke up and said, "You know what medicine lacks? A deeply confusing mouse." The real goal was reconstructive medicine. If you can grow cartilage in a controlled shape, then maybe one day you can help children born with malformed outer ears, patients injured in accidents, people needing reconstruction after cancer surgery, anyone who needs tissue replacement without relying on donor grafts or painful tissue harvesting from elsewhere in the body. That's the bigger vision. Medicine has always had a supply problem. There are more damaged tissues and organs than there are ideal replacements. So tissue engineering is, at its heart, an answer to a painfully human question. What if we could build replacement parts that are living, compatible, and shaped exactly for the patient? Not machine parts, not crude substitutes, living structures. And that is where the story shifts from spectacle to significance. Because the ear on a mouse was not the destination, it was the billboard on the road. Act 6. The science kept moving. The famous mouse became an icon in the 1990s, but the field did not freeze there. It kept evolving. Researchers continued developing ear-shaped cartilage engineering, improving scaffold design, mechanical stability, biocompatibility, and clinical translation. Later work reported patient-specific ear-shaped cartilage using biodegradable scaffolds and expanded chondrocytes. And studies have described auricular reconstruction in microtia patients with encouraging aesthetic outcomes in early follow-up. That is the arc of real science. First, a shocking proof of concept, then years of less glamorous refinement, then, if everything goes well, real-world application. The public remembers the weird mouse. Science remembers the iteration. Because the hard part is rarely the first dramatic image. The hard part is everything after the headline, making it safe, making it reproducible, making it durable, making it work in actual human bodies, not just promising lab models. Science is full of wow. Medicine is built on, does it still work after 2 years? Act 9. The philosophical punch of tissue engineering. Now let's go deeper. The philosophical punch of tissue engineering is this. Form is not decoration. Form is instruction. Cells are not just passive blobs waiting for chemistry. They respond to environment, physical cues, mechanical stress, spatial arrangement, neighboring cells, the 3D environment around them. In other words, biology is not just code, it is also context. We live in an age obsessed with information, genes, sequences, programs, instructions, and yes, those matter. But the ear on a mouse story reminds us that placement, shape, and physical structure matter too. Give the right cells the wrong environment, and they fail. Give the right cells the right scaffold, and suddenly biology starts cooperating. It's almost like life doesn't just need ingredients, it needs architecture. And if you zoom out far enough, that lesson stops being about cartilage and starts sounding suspiciously like a principle
for civilization. People, like cells, respond to environments. Build bad structures, get chaos. Build good structures, and surprising forms emerge. Yes, we started with a mouse. Now we're discussing metaphysics. That's what a good rabbit hole does. Act 8. The humor and horror of scientific progress. Let's be honest. Part of why this story survives is because it is the perfect collision of genius and nightmare. It looks like a prop from a low-budget sci-fi film called Honey, I Grafted the Kid. It's the kind of image that makes your aunt say, "This is why I don't trust people with PhDs." But science often advances through moments that look absurd, before they look obvious. The first heart transplant once sounded impossible. IVF sounded unnatural to many people. Lab-grown tissues sounded grotesque. Then time passes, technique improves, context catches up, and yesterday's horror poster becomes tomorrow's medical textbook. That doesn't mean every strange experiment is wise. It means weirdness by itself is not a refutation. Sometimes the frontier looks ugly before it looks useful. Sometimes the first draft of the future is visually offensive. Act 9. What this means for the future. So where does this road lead? The dream of tissue engineering is bigger than ears. It points toward a future where scaffolds, biomaterials, and patient-derived cells may help create or repair cartilage, skin, bone, blood vessels, and eventually more complex tissues. That does not mean we are casually printing perfect spare organs on demand next Tuesday. Complex tissues need blood supply. They need mechanical integrity. They need immune compatibility. They need long-term function. The closer you move from simple shapes to fully functional organs, the harder the mountain becomes. But the principle remains. If you can control the microenvironment, you can begin to guide living matter. And that may be one of the most consequential powers medicine is learning. Not domination over life, not magical creation from nothing, guidance. A scaffold is, in a sense, an invitation to life. Here, grow this way. So the next time someone says, "Didn't scientists genetically engineer a mouse to grow a human ear?" you can smile and say, "Not exactly. What they saw was stranger in a more intelligent way. It was tissue engineering, a biodegradable scaffold, cartilage cells, a living host, and one unforgettable image that taught the world a difficult truth. Sometimes science doesn't change life by rewriting the code. Sometimes it changes life by building the right frame and letting biology do what it has always wanted to do. The mouse carried the headline. The scaffold carried the future. And that, my friend, is the difference between a viral image and a medical revolution. If you want more stories where science looks like fiction until you understand it, subscribe. because the future is not just coming, it's being grown, sometimes on a scaffold, sometimes in a lab, and occasionally in a way that terrifies the internet first.